This is lesson 14, proving lines perpendicular. The objective is to prove and apply theorems about perpendicular lines. The vocabulary words are perpendicular bisector, distance from a point to a line. The definitions: the perpendicular bisector of a segment is a line perpendicular to a segment at the segment's midpoint. The shortest segment from a point to a line is perpendicular to the line. This fact is used to define the distance from a point to a line as the length of the perpendicular segment from the point to the line. Let's look at what that means. We have this triangle, ABC, and we have P somewhere along BC, and we see that it is perpendicular to BC. To name the shortest segment from point A to BC, we look for the perpendicular bisector. It is the perpendicular segment, so it is the shortest distance. If we were to travel from A to C, we would see that this is even visually longer than AP. And of course, AB is much longer than both of those. So your answer would be BC. AP is the shortest segment to BC. If we want to write and solve an inequality for x, since we don't really have an exacting value, we can at least figure out what it kind of would be. Since AP is the shortest segment, then AC is greater than AP. And AC is x minus 8, so we're going to substitute this in, and 12 represents AP. So our inequality would be x minus 8 is greater than 12. But we can simplify this, add 8 to both sides, and we get that x is greater than 20. Now you try. Name the shortest segment from point A to BC. Did you say AB? Write and solve an inequality for x. Well, AB is the shortest. AC is greater than AB. Did you substitute in? Should have had 12 is greater than x minus 5. Add 5 to both sides, and 17 is greater than x. Here are some more theorems for your list. We have theorem 341. If two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So two intersecting lines form a linear pair of congruent angles, and the lines are perpendicular. We have 342, the perpendicular transversal theorem. In a plane, if a transversal is perpendicular to one of the two parallel lines, then it is perpendicular to the other line. If two coplanar lines are perpendicular to the same line, then the two lines are parallel to each other. This is kind of the inverse of the perpendicular transversal theorem. because you're looking at the parallel lines. We know they're parallel. That means that if the line is perpendicular to one, it's perpendicular to the other. And then for 3, 4, 3, if we have two coplanar lines perpendicular to the same line, then they are parallel. So just like we were looking at in lesson 13, this is what we use to prove things parallel. Let's prove properties of lines with a two-column proof. We're given that R is parallel to S and that angle 1 is congruent to angle 2. Let's prove that R is perpendicular to T. So, first of all, we state the given. R is parallel to S, and angle 1 is congruent to angle 2. This is given to us. Second, we know then that angle 2 is congruent to angle 3 by the corresponding angles postulate. Angle 1 is congruent to angle 3 from the transitive property of congruence. And R is perpendicular to T because two intersecting lines form linear pairs of congruent angles. The lines are perpendicular. Now you practice. Write a two-column proof. You are given that angle EHF is congruent to angle HFG, and that FG is perpendicular to GH. You want to prove that EH is perpendicular to GH. Work that out and then continue the video. You should have said that angle EHF is congruent to HFG. This was given. And that you have EH is parallel to FG by the converse of the alternate interior angles theorem. Then FG is perpendicular to GH because it's given. And therefore, EH is perpendicular to GH by the transversal theorem, the perpendicular transversal theorem. Remember, if it is perpendicular to one of the parallel lines, it is perpendicular to the other. Let's look at a real-world example. A carpenter square forms a right angle. A carpenter places the square so that one side is parallel to an edge of a board and then draws a line along the other side of the square. Then he slides the square to the right and draws the same line. Why must the two lines be parallel? So let's look at this picture. He's drawn a line here and a line here where the two squares are shown. Why do they have to be parallel? Well, we notice these little red corners that show that they are perpendicular. It's a right angle. Both of these carpenter squares are hitting the board at right angles, and it's the same line. So that must mean, since these make right angles, that these are parallel lines. Both lines are perpendicular to the edge of the board. If two coplanar lines are perpendicular to the same line, then the two lines are parallel to each other. So the lines must be parallel. Now you practice. A swimmer who gets caught in a rip current should swim in the direction perpendicular to the current. Why should the path of the swimmer be parallel to the shoreline? Work this problem out and then start the video again. If you look at the answer and the picture, we have that the shoreline and the parallel line, the line to the perpendicular to the rip current itself, are parallel lines because they're both perpendicular to the same rip current. The shoreline and path of swimmer should be perpendicular to the current, and that means they'll be parallel to each other. Let's look at some problems. Name the shortest segment from point K to Ln. Did you say Km? Let's write and solve an inequality for x. We know that Km is less than Lk, or KL. So we would say 14 is greater than x plus 5. Then you would subtract the 5 from both sides, and you get x is less than 9. Looking at 3 and 4, we'll use the bottom figure. Name the shortest segment from point Q to GH. Well, we don't know what x equals. We do know that QH is perpendicular. It has to be the shortest segment. So QH. And we want to write and solve an inequality for x. This time we know that x minus 2 is greater than 9. So we end up with x is greater than 11. Let's try another proof. We are given angle 1 is congruent to angle 2, and line S is perpendicular to line T. And we want to prove that R is also perpendicular to T. So the first line says that angle 1 is congruent to angle 2, and that's given. So what can we say if we're using the converse of the alternate interior angles theorem? Let's look at these. Well, R is parallel to S. We can see this because the angles are congruent, and they are cut by the same transversal. Then we have S is perpendicular to T. That's given. Therefore, R is perpendicular to T. Remember what we said, if a line is perpendicular to one of two parallel lines, it must be perpendicular to the other one. And that is the perpendicular transversal theorem. So remember, to prove angles congruent, use transversal theorems and postulate. But to prove lines parallel, use the converse of transversal theorems and postulate. And to prove lines perpendicular, use the perpendicular transversal theorem. For next class, please complete the graphic comparing and contrasting how you prove lines parallel and proving lines perpendicular. I'll see you in class.